function of time, and it has so many applications, including ship navigation, loading and offloading of vessels, things like floating liquefied natural gas production facilities, then mitigation loads on floating wind turbines, up to alleviating gas loads due to waves on marine current turbines, and optimal control of wave energy converters, which is our main focus in the research center here. So it is, from previous studies, it has been shown that wave prediction plus active control on wave energy converters can significantly maximize the power output by about a factor of 2. And we are using Fourier transforms to carry out this prediction, and it can sort of give us a few tens of seconds of future prediction. And I'm going to show that the prediction becomes harder with directional spreading. And the aim here is to predict 2 to 3 wave periods, which we think are going to be enough for control of wave energy converters. But we are using a unidirectional scheme in weakly spread seas, typically less than 10 degrees, described by the standard deviation of the Gaussian distribution function. And we use surface elevation time histories as input into this model. So the waves are generated on the computer using a 2D spectrum, which is a KOZWaves spectrum multiplied by a frequency-independent rep normal spreading function, which is equation 1 here. And then this is the equation for synthesizing the free surface waves, is number 2 here. And then K is the wave number, and X is the position. These two are vectors, and this is the dot product of a vector. And this is the radiant frequency, and this is time, and this is the initial phase shift. So we're just summing over different frequency components and different propagation directions. So this is what surface elevation looks like in 3D. So we'll be having wave buoys offshore of the wave energy converters or the intended prediction point, sort of measuring the displacement of the ocean surface. And then we are predicting somewhere here where these red spheres are. These are wave energy converters in my case here, but you can predict for whatever you want to predict for. And the prediction looks something like this. So I'm just showing the time series plot of the prediction at the wave energy converters locations that I just showed before, the red spheres. So this is the spreading of 10 degrees. So this is the maximum spreading for this model here, because we are intended in very accurate, we intend to get very accurate predictions. So we're just taking this one as the worst case. And these lines here, the 2 vertical lines, are indicating the predictable zone as a zone in which you could get reliable predictions. So this is the end of the predictable zone where the green line is here, which is described using the fastest wave component in the spectrum. So, and yeah, as you can see, the waves are propagating towards the predictable zone here, and we are starting to get good prediction between 0 and 2.2 peak periods. So I'm just going to walk you through quickly the theory behind the prediction model that we are using. We're just using a unidirectional model to propagate waves that are directional, like waves from directionally spread seas, but with weak spreading. So we first assume a plane wave component, which is propagating at an angle phi, with frequencies, with just a single frequency from a Dirac delta spectrum. And we are in deep water, so we're using the linear dispersion omega squared is equal to GK. And then now we consider another component, which is propagating at a slightly different angle theta and slightly different frequency omega at n, which is in this narrow bandwidth here, delta omega. So we just calculate first the average waveform, which is given by this C bar in over the narrow bandwidth, and then we get cosine and sine Fresnel integrals down here. This is a very bulky term, but as we go forward in time, this tends to 0 at longer times and longer distances. And then we now calculate the non-dimensional estimate variance, which is the variance of the component we use to represent the propagation of the C state relative to the average waveform, the C bar that we calculated in the previous slide, over the narrow bandwidth delta omega, which is given by this. And then because we are going to get Fresnel integrals when we integrate something like this with omega squared, so we just expand this in t to like order of t squared, and then we substitute back the x and t. So we start replacing x by this with m as a parameter, and then we substitute back, and then we take the integral, and then we expand again. This is Taylor expansion, and then we expand again in delta omega. So we get the NEV looking like this. So the first term here is dominated by directional errors. Yeah, and then the second term, which is this one here, is dominated by frequency errors. And you can see the group velocity is coming in here, which is indicating, which is telling us the importance of group velocity in wave propagation. Some of the terms that I just dropped are still in delta omega squared. They are very small. They are like quartic in bandwidth, and we are like considering short distance predictions because we don't want to like predict very far, and the prediction error grows rapidly with distance and time. So we are very close to the measurement point. And what we do first to eliminate the phase here, so we just use half because this is like half a unit circle, sine squared. And then this term here is almost 1, like a typical wave frequencies and typical frequency resolutions. So this is replaced by 1, and then this is what we get next. So this term is now looking like this. So we have dropped all the other terms, and we're just having the 2 terms that I just talked about before. So now we integrate over the whole frequency bandwidth. So we assume a band limited spectrum with the lower frequency omega L and the higher frequency omega H. So we integrate the 2 terms that I showed in the previous slide, and we get something which is looking like this k bar squared x squared times the directional terms, and then the frequency terms coming in the second term here from the mean value theorem for integrals. And then this k bar is the average wave number, and CG bar is the average group velocity. So as I said, that we are interested in predictions close to the measurement point. So we are going to focus on the first term. So the first term here, which has cosine phi and cosine theta. So we Taylor expand that in phi and in theta, and then we just get this phi squared minus theta squared in brackets and all of these. And now we just calculate the variance over all directions, assuming that the mean wave propagation is 0. So that's the first assumption. So we use the Gaussian distribution or the rep normal spreading function to describe the propagation direction. So we integrate from minus infinity to infinity. So we just put the directional term here first, like we just drop the k squared and x squared because they have nothing to do with direction. And then this is what we get. And when we minimize this, the variance, because the variance is pretty much the measure of error. So we get solution phi is equal to plus minus the standard deviation of the rep normal spreading function. So it tells us that we have to propagate the waves at an offset angle of sigma, which is the standard deviation of the Gaussian distribution function. So this is the one which gives us less errors when we propagate the waves based on assuming that the mean wave direction is 0. So if you substitute this back into the variance, we get this term sigma to the 4 on 2. And now we just want to find the general solution. So we assume that the C state doesn't have to be 0 degrees. And we again integrate over all the possible propagation directions, and we get the variance looking like this. And when we minimize this, we are going to get phi is equal to theta bar squared plus sigma squared raised to the power half. So this tells us this is the general solution, and if the mean is 0, so we get back the form that I showed in the previous slide. And this angle has been validated numerically. We just generated data on the computer, and then we sort of showed that this is the best propagation angle. We're just trialing so many different angles, and this one proved to be close to the numerical solution. So that's, yeah, it does work. And then we substitute back phi into the nav, we are going to get this. And this is the additional term, like what we saw before was these ones in black. And now we are having this term. So this tells us that we get more prediction error when we place the prediction point away from the mean wave direction. So yeah, so we are using Fourier transform. So the propagation now is just looking like this. So we just take the Fourier transform of like the time history that we have measured at the point x0, and then we just propagate based on this. This is the transfer function which relates the amplitude at the measurement point and the prediction point using the phi that we have derived. Here I'm just showing the effect of varying the mean wave direction and the spreading on the prediction. So this is a very small spreading, 1.4 degrees. And then I'm just varying the mean direction like between 0 and 10 degrees. So you can predict like this is pretty much long crested waves. And as you increase the spreading, you can see here that is like a significant effect of the varying mean wave direction, so on and so forth, up to like 8.6 degrees. So you can see when it is 10 degrees away from the prediction point that the errors are increasing significantly. So what we do now to increase the tolerance to the varying mean wave direction, we just aggregate measurements from different wave buoys. So I'm just using wave buoys to indicate like any measurement device that you would use at the measurement point, but you can use anything that can measure the surface elevation there. So we are just using this concept, which is the wisdom of crowds, but it is formally known as the inverse variance weighting. So we just consider a set of measurements that are normally distributed, and then the probability of getting back the whole set is multiplying the whole probabilities. And if each of the predictions is described using the Gaussian distribution, so you're going to get this. And maximizing this, you just take the derivative of the probability and with respect to the average. So we are going to get the average prediction described by this summation here, which is like the variances of each of the predictions. But we have calculated the variances already, which is our nav in the slides before. So the main result is now this. So we're just going to weight each of the predictions based on the corresponding non-dimensional estimated variance. So I'm using 3 and 2 wave buoys to illustrate that the tolerance in varying mean wave direction is increasing. So I'm just doing these contour plots here. I was just using 2. So you can see here that even when the top 2 plots here are actually using the inverse variance weighting, and then these ones are just using single wave buoys. But depending on the mean wave direction, I'm just taking the buoy which is closer to the propagation direction there. But yeah, if you look at the contour, the one with 0.1 here, so it is covering a spreading which is plus minus pretty much like 8 degrees. So, but as you can see here, when the waves are propagating at 0 degrees, like the mean, the prediction is poor until it is actually in line with one of the wave buoys, either the one below or the one at the top. So with the aggregating, it does improve the prediction in this way. And I'm just showing the cross sections of these contour plots, this side on the right here. So the weighted prediction is, it doesn't get worse even when the waves are propagating along the the line connecting one of the wave buoys and the prediction point, as you can see in the bottom plot here. So it is equally good compared to the prediction from a single wave buoy, which is in the best position when the waves are propagating at 7.5 degrees and the theta p is 7.5 degrees as well. But everywhere else, the inverse variance weighting is better. So these are just time series plots.
Sorry, Thobani, but you just have a minute left.
Okay. These are time series plots that I did with 3 wave buoys. So you see the prediction is pretty much the same up to like 15 degrees mean wave direction. And for like practical applications, we are studying, we are using Hlophe as our study site. So it has these wave conditions here. The mean is less than 10 degrees in more than 50% of the time, and the waves are coming in at 210 degrees. So, which is like plus minus 7.5 deflection for more than 70% of the time. So we can apply this model in Hlophe and anywhere along the south coast of Australia, but we don't think it can work in the northeastern North Atlantic. And the computational time is less than 1/10 of a second. So these are my conclusions. I've just shown that there is an effective offset angle that we can use to propagate the waves, and I've shown that the directional spreading contributes significantly in the prediction errors and the misalignment of the prediction point and the measurement point as well. And I've shown that we can increase the tolerance by using the inverse variance weighting, which is just 2 or more wave buoys. And I've shown that the model can work along the south coast of Australia. Thank you very much. These are just references that.
Thank you. But at least you are there, you get the applause. Okay, Thobani, very nice presentation again. Any questions from the audience? Yeah, the first talk in the audience is a bit shy. Thobani, one thing I didn't get, what exactly is your directional distribution? What directional distribution did you use in your model?
I'm using the rep normal distribution. Is that the spreading function that you're asking?
Yeah, for? I think you showed the equation at the beginning.
Yeah, I'm using the rep normal spreading function, which is just the Gaussian distribution function, equation 1 here.
How you cannot change with this one? You cannot change the spreading.
The spreading is described by this standard deviation sigma theta here, so I can change it.
Okay. I'm not familiar with this one. Okay, I missed that part. Yeah, because as you say in your conclusion, the spreading can play quite an important role. It's an important parameter. Yeah. All right. Any other questions? Time for at least one question. Okay, if not, Thobani, thank you very much for your presentation. And I thanks all the speakers of this session for staying on time. And we will have, well, I'm not sure what I'm trying to have virtually, but we will reconvene in 12, what time? Sorry.
Sandro, we're
9:30 Perth time.
Yeah, we're going to have some breakout rooms.
Thank you.
So thanks, Alessandro.
Yeah, no problem.
We're going to have some breakout rooms, so for a chance to discuss